You probably use a digital wallet every single day. You pop open an app, you see a number, and you trust it. But have you ever stopped and wondered what that number really is? Today, we're going to dive into the hidden engineering that keeps your digital money from just disappearing. And believe me, it's a lot more complex and way more fascinating than you might think.
So let's start with a question that sounds almost ridiculously simple. Your app says you've got 50 bucks. Okay, but what is that number? Is it just a little file on a server somewhere? A single cell in some giant spreadsheet? The answer, it turns out, isn't just a fun little piece of trivia. It's basically the foundation of our entire digital economy.
All right, to really get why the right way works so well, we first have to look at the wrong way. It's the approach that seems totally logical at first glance, but as you're about to see, it's a simple idea that is also incredibly dangerous. Now, your first guess might be that your balance is just a single number sitting in a database, kind of like a number you'd write on a whiteboard. Super easy to see, super easy to change. But the reality? It's so much more robust. It's actually a complete, unchangeable history of every transaction you've ever made. Think of it more like words being carved into a stone tablet. You don't erase the past, you just keep adding to the story.
So why is that simple guess so dangerous? Well, think about it for a second. What if there's a tiny glitch during an update? Or what if two different requests try to change your balance at the exact same time? A system built that way it's incredibly fragile. It would be a total recipe for disaster, corrupted data, system-wide errors, and, worst of all, people literally losing their money.
So, okay, if it's not just a single editable number, then what is the secret? Let's pull back the curtain and reveal the core principle that makes every secure digital payment system, from Apple Pay to PayPal, actually work without falling apart. And here it is. This is the single most important idea in all of financial engineering. You never store the balance as a single changeable thing, ever. Instead, you store a permanent, unchangeable list of every single transaction. So that balance you see in your app, it doesn't actually exist in a database anywhere. It's calculated fresh from scratch every single time by just adding up your entire transaction history.
This whole system is built on this really powerful, centuries-old accounting idea called the double entry ledger. All it means is that money is never just created out of thin air or destroyed. For every single debit from one account, there has to be an equal and opposite credit to another account. So if you lose $10, somebody else has to gain $10. The net change is always zero, and that's what prevents money from just magically appearing or disappearing because of some weird bug. So we've got this classic, time-tested accounting concept. Now, let's see how engineers take that idea and turn it into a modern digital fortress, an architecture that can handle millions of transactions all happening at once.
The second you hit send, your request goes on a little journey. It starts at your app, shoots through a gateway, and hits the main wallet service. But the most important stop, the real VIP of this whole trip, is the ledger service. This thing is the system's brain. It's the single source of truth. It ignores everything else and it only asks one question. What does the permanent transaction log in the database say? That's it.
Okay, let's zoom in even closer. What is actually happening in those few seconds it takes for you to pay your friend back for coffee? Let's follow the money, step by step, for just one single payment.
It's this super fast sequence of checks and balances. First, your app sends the request with a unique key so you don't accidentally pay twice. Then, the system temporarily locks both accounts, yours and your friend's, so nothing else can mess with them while this is happening. It checks to make sure you actually have the money, and only after all of those checks pass does it permanently write the two entries to the ledger, a debit from you, a credit to them. Done.
Now this final step, the actual writing to the ledger, has to be what we call atomic. And this is a hugely critical concept. It just means the transaction is all or nothing. It's like a light switch, right? It's either fully on or fully off. There is no in-between. So if the system crashes for even a millisecond during that write, poof, the entire transaction is instantly erased as if it never even happened. This makes it literally impossible to leave the financial records in some kind of broken, unbalanced state.
Okay, so this process works perfectly for one transaction. But what about a million of them, all trying to happen in the exact same second? How does a system like this scale up and defend itself from all sorts of digital attacks?
This is such a classic problem in computer science. It's called a race condition. Just imagine you have $10 and you try to send that same $10 to two different friends at the exact same millisecond. How does the system stop you from spending money you don't have?
Well, engineers have a few clever tricks up their sleeves. The simplest one is just locking your account for a split second, but that can really slow things down. A fancier way is something called optimistic concurrency. where the system just tries the transaction and hopes for the best. If two conflict, it just cancels one and tries again. But for truly massive scale, the industry standard is sharding. This basically means splitting all the users across many different servers. So your transaction and one happening on the other side of the world are handled in parallel. They never even have to compete with each other.
You ever done this? You hit send, your connection drops, and you frantically start tapping it again and again. So why didn't you get charged 5 times? The answer is this really powerful idea called idempotency. Remember that unique key that gets attached to every request? Well, the server remembers it. If it sees that same key pop up again, it knows, hey, I've seen this before. This is a duplicate. It won't process the payment again. It'll just send you back the confirmation from the first time. Pretty cool, right?
All right, we have gone deep into the weeds of the architecture, so let's pull back up for a second and boil all of this down to the core concepts, the big ideas that really define a professional, secure, and scalable digital wallet.
Look, if you remember just one single thing from this entire explainer, please make it this. This is the senior level way of thinking that changes how you see the entire problem. You're not just updating a number in a table. You are maintaining the integrity of a massive, distributed accounting ledger. It's a whole different ballgame.
So let's put it all together. The foundation? An append-only double-entry ledger. You always derive balances, you never store them directly. You shard your accounts to handle massive scale. You use idempotency and atomic commits to make sure every single transaction is perfect. And above all, you prioritize financial correctness over being available 100% of the time. Because when it comes to money, being right is always more important than being fast.
So the next time you tap your phone to pay for something, you'll know about the incredible, invisible system that's working behind the scenes to protect that transaction. It's just a powerful reminder that behind our simplest clicks and taps, there's often a world of truly amazing engineering. And it kind of makes you wonder, right? What other simple tech that we use every day is secretly this complex?